Hello, my name is Brian Sanchez, and in this video, I'll be describing ENPM809T, Autonomous Robotics. ENPM809T is intended to be a hands-on course in which the principles of autonomy in robotics are explored and even implemented in the final project, called the Grand Challenge. I'll be giving details about this challenge later on in the video, but first, what exactly is autonomy? As defined by dictionary.com, autonomy can be described as independence and freedom over one's actions. In other words, having the ability to act and make decisions without external influences. Throughout this course, we explored the concepts in which autonomy can be implemented in robotics, specifically in our ground-based robots, and how it is already being implemented by companies today such as Tesla's autopilot feature and Amazon's autonomous delivery service. These concepts of autonomy include perception, localization, planning, and decision-making. Each student was required to obtain a parts kit, which would allow every student to uniquely build and code their own robot. For this course, the language of choice was Python, which was used in conjunction with the Raspberry Pi, a microcontroller used as a tool to send and receive information from the robot's sensors and actuators. The course essentially builds on itself, with the intentions of equipping every student with the necessary skills to complete the Grand Challenge. The theme of the Grand Challenge came from SpaceX's future goals of sending cargo to Mars to serve as the first Mars base that humans would be able to use as shelter. As a continuation or test of this goal, the Grand Challenge serves as a simulation of constructing this base on Mars. Students are required to utilize material covered in the course to create an algorithm in order to efficiently and autonomously navigate through the cluttered environment, find the cargo that has been scattered throughout the simulated surface of Mars, and transport it to a predetermined construction area to aid the construction of the base. This task is completed by integrating sensors and actuators into the mechatronic system that is our ground-based robot. Specifically, the use of image processing, motion control, and planning were extremely important to understand in order to be able to complete the task. The hardware of the robot includes both mechanical and electrical components. The mechanical components include the wheels, servo motors, gripper, and overall platform that holds the robot together. The overall robot platform provides a sturdy structure for the various robot components in order for them to perform their respective tasks. For example, the compartments and screws used to secure the wheels and motors to the body offer the motors the advantage of being able to supply torque to the wheels in order to put the robot in motion, thus being able to move. The gripper makes it possible to pick up and transport the cargo. Electrical components include the Raspberry Pi, which in general is used to send and receive information from the robot, a Pi camera for recording images and videos of the environment, wheel encoders to monitor the motion of the servo motor shafts, a sonar range sensor to measure distances, a battery pack to serve as a voltage supply, batteries, and an H-bridge to control the direction of spin on the wheels. As said previously, this course progressively builds towards being able to complete the Grand Challenge. Every capability of the robot was explored and tested one by one. In the beginning of the course, a brief introduction and tutorial on Python was given, as well as a few assignments to confirm that the necessary coding skills were developed in order to effectively communicate with the various components of the robot and adjust its behavior based on this information. The Pi camera that would soon be mounted onto the Raspberry Pi was introduced by being asked to simply take images and recordings to ensure that a good connection between the Raspberry Pi, Pi camera, and laptop was made. After having done this, the concept of image processing was introduced, where different actions could be performed on images, including color segmentation, drawing functions, and more. In the final project, I will be using color segmentation to identify the different colored blocks, as well as its position in the image, which would allow for decision-making, motion planning, and spatial awareness. This concept can be seen in the following assignment, where HSV masks and contours were applied to the images, one by one to perform object tracking and orientation classification. The outputs on the right show the flow of this process. First, the image is converted to HSV, then given lower and upper color bounds to specify a desired color of interest, turned into black and white in order to identify any contours, and lastly, the desired shape to be drawn on this contour is drawn on the original image. The sonar range sensor was introduced by being asked to record an image with the PI camera, while at the same time using the sonar range sensor to send and receive a signal and interpret the time duration of that signal and convert it into a measure of distance from an object. This exchange of information and calculation was conducted using Python by specifying voltage values, duration values, and equations. The next component to be explored are the motors of the robot, along with the H-bridge, which control the direction of spin of the wheels and include forward, reverse, pivot right, and pivot left. The direction of movement can be specified according to the values assigned to a set of pins on the Raspberry Pi. These behaviors can be seen in the video. Note that these actions are not perfect and will be corrected shortly after when the encoders are introduced. The next functionality to be added onto the robot is the gripper. The orientation of the gripper is controlled by a servo motor that rotates according to the duty cycle specified by the user. As previously stated, this functionality is used to pick up and drop the cargo in the simulation. To fix the performance of the robot's motion, encoders have been introduced, which turn mechanical movement into digital signals. In this course, the encoders will monitor the movement of the motor's shafts and send this data to the user, which can be used to adjust how much a pair of wheels spin. For example, a curved path is caused by a set of wheels moving at a higher rate than the other, and can be corrected by either slowing down the wheels going too fast or increasing the speed of the slower wheels. This difference in wheel rotations are largely caused by different amounts of friction. The next assignment aims to put many of these functionalities to use at the same time. Here, I chose to use the gripper, wheels, wheel encoders, and Pi to work together in order to track and retrieve the cargo. Having recorded an image, I used the center of the object's contour to determine the angle needed to be turned so that the center of the camera would be aligned with the object. I then used the contour center's position in the image to determine how much the robot should move towards it. Similarly, I specified the gripper to open and close if the contour was within a certain range in the lower half of the image. I then backtracked in order to go back to the starting position. It's important to note that there are crucial differences in regards to the environment in which the robot is operating in. Since the grand challenge would take place in the robot realization lab, I tested my algorithm by running it through the arena multiple times in order to obtain the correct parameters, since the lighting and surface floor textures are very specific and could potentially vary in another setting, which would result in reduced accuracy or increased wheel slip during the grand challenge. During the testing phase, I encountered a few challenges. The first being that my Python program would crash, giving a segmentation fault error as a result of too many commands at once, causing the robot to stop wherever it left off at. The video on the right shows the robot spinning in circles as a result of such a crash. I was able to reduce the likelihood of this error by adding small pauses in between commands to ensure enough time for commands to be executed. I also encountered premature closing of the claw before the cargo was within reach, as well as knocking it over to the side, which was caused by approaching the cargo too fast. Both of these issues were solved by decreasing the amount of distance covered when approaching the object, which allowed for more accurate readings and almost eliminated the chance of knocking the object over. During the Grand Challenge, I was able to successfully retrieve and transport 4 blocks as well as dragging an incorrect one to the construction zone. Because of the error propagation in terms of changing the orientation of the robot by pivoting, the accuracy of the coordinate system after the first block decreased incrementally, causing the cargo position coordinates to be slightly off.